this one. We already did this one because we did silver with nitric acid as the example.
No.
Is that? No?
We did copper with sodium nitrate and then nitric acid.
And nitric acid, okay. We're going to do this one then. Silver solid. But, you know, the only problem is that I don't have, obviously there's not enough time to go through and lecture about everything again. So what you want to do is you want to go through your notes and see what you're shaky on. And then, you know, obviously we have time to review certain topics, but not everything. Okay? And so in preparation for the final, just see what you're shaky on, and then we'll focus on those rather than doing broad breath review. And so when we inventory this, we have silver ions, we have H+, we have nitrate, and we have water. It's inventory. And so we don't have silver ions. There's a big difference between silver metal and silver ions. They aren't the same. This is something that people always do. They say silver metal is the same thing as silver ion. I don't know why they always do that. It's like sodium metal and sodium ion. It's that Dr. Jekyll and Mr. Hyde thing. So the people think that they're the same. They aren't the same. This is silver metal. And so silver metal is a reducing agent. Silver ion is an oxidizer. Silver metal is a poor reducing agent. Silver ion is a strong oxidizer. H+ is an oxidizer. Nitrate is an oxidizer when combined with H+. So H+ alone is an oxidizer. Nitrate and H+ is an oxidizer. Water is both an oxidizer and a reducer. So we pick the strongest reducer based on the chart and the strongest oxidizer based on the chart. Those are the two that are most likely to react. Then we go to the chart and just copy the reactions off the chart. So silver goes to silver ion plus an electron. And then nitrate, these are just copied off the chart. Nitrate plus 4H plus 3 electrons yields NO plus 3H2O, 4H2Os, 2H2Os. Yeah, we got to balance out the electrons. So the easiest is to multiply the top one by 3. So we're going to get 3 silvers plus nitrate plus 4H plus. Okay, 3 electrons here will cancel 3 here. So I'm not even going to write it down. This is going to go 3 silver ions. Those 3 cancel plus an NO plus 2H2O liquids. Gas. Silver solid. Then what?
You have to determine driving force?
Yeah. And so the easiest way to determine driving force is from up here. This is the RA. This is the conjugate OA. This is the OA. This would be its conjugate RA. So we do the conjugate pairs. You know, in one direction it'd be the reducing agent, the opposite direction would be the oxidizer. You know, if we think of these reactions can go either way. This is why I wrote this one backwards, or this one backwards, you know, from what the chart shows. Depends on which chart we look at. So RA, OA, OA, RA. And then we consult the chart and see which one's stronger. It turns out that nitrate with H+ is stronger oxidizer than silver. Not much. This is stronger. So we have driving force. Now this one we don't write the complete, the ionic and the net ionic equation for. Yeah, this one automatically yields net ionic, and this is where we'd stop. We'd stop with the net ionic equation for this. But you know, just think how, you know, it's really important. Let me just emphasize this. That you know, I don't know what your approach to studying is. You know, if your approach is just to review the book, if you just review the book, you're going to have trouble in what are called upper division classes at the university. The upper division classes have books that are 1,000 pages long that are covered in 10 weeks. You can't review the book. It's too much material way too much material. And so you have to have notes that you review. Whether you make the notes yourself or you get them from lecture, you need something that's a little bit less than everything that the book covers, because there's not enough time to cover everything in the book. And then you got to commit those to, if you have notes but you never review your notes, then it's not that useful. So you got to review those regularly, and that'll make a big impact, I think, on the studying. Because, if you just review the notes from day one to the present day, whatever notes you have, then things will stay fresher in your memory. You'll remember the methods. But those are just some tips. You can study any way you want, of course. If you can't remember the alternative to single replacement would be a chart method, and you wanted to make sure it's a little fresher.
The chart method works for all reactions, couldn't you? Or no?
Yeah,
Okay.
chart method works for all reactions. Single replacement doesn't.
Yeah.
So you got to know the exceptions for single replacement. That was one of the key exceptions when we have an oxidizing acid. Tomorrow we'll look at another key exception for the single replacement. Do you know? Maybe you already know it because I talked about it in lecture. Does anybody remember what that other key exception is? See, if you can't recall it like this, then you're going to have trouble on speed tests. Did I tell you at UCLA most of the exams are tested? It's like this. They have somebody watching the clock, and everybody has to have their pencil down. When they call time, then you can lift your pencil off the table. You can't look at the exam before, and everybody has the exact same amount of time, and nobody finishes. And so it's a speed test. They reward speed. And so these things, if you can't recall it fast, then you're at a huge disadvantage. I learned that. I learned that the hard way, because when I went there, I wasn't much of a speed. I didn't think much of speed, I didn't really study for speed. But you need rapid recall for speed. If you don't have rapid recall, you can't recall, certain things fast. You're going to be at the bottom of the curve. Bottom of the curve is not a good place to be. Everybody else is training for speed, however they can.
The other exception, skeletal redox?
Skeleton redox is a totally different thing, because with skeleton redox, we don't have to predict the products. I'll tell you what the other exception is. I'm not going to leave you hanging. It's something like this. If we had chlorine plus sodium bromide, this kind of looks like, A plus BX, but A plus BX will fail for this. Why will A plus BX fail? It's because single replacement automatically defines each participant's role. Like single replacement says A must be the
reducer.
A must be the reducing agent. And so, and then B must be the oxidizer. And X is the spectator. So in the last example, the reason why nitric acid failed is because X is not a spectator. X is the strongest oxidizer present. The reason why this fails is because chlorine, is that a good reducer? No. In fact, chlorine is a powerful oxidizer. And sodium ion, is that a good oxidizer? No, sodium ion is not. So this has it all assigned wrong. And so single replacement is going to fail if the strongest oxidizer is not B and the strongest reducer is not A. And so in this case, it totally fails. And so in Chem 1A, they give you another pattern to memorize. The other pattern is called the X2 plus BY pattern. the x2 plus by yields y2 plus bx. This only works for this type. So you'd memorize this pattern too, but no reason to memorize, because for every exception, do you want to have to memorize a pattern? No, we'd rather just use the chart method. The chart method, you don't have to worry about this. It's just, if you want to do single replacement, you have to worry about this. Single replacement has a huge advantage though. Single replacement's fast and it's easy. It has a huge disadvantage though. The huge disadvantage is unless somebody pruned out all the weeds, unless somebody pruned out all the thorns, you're going to get stuck by a thorn, if you're not careful. But, somebody can de-thorn. So if somebody goes in there and clips all the thorns out, somebody goes in there and eliminates all the reactions like this, and they go, well, nitric acid, you don't need to know nitric acid. When they eliminate nitric acid, then single replacement is fine, But that's de-thorning it, Unfortunately, your instructor might be nice at de-thorning, but other scientists aren't nice. Other scientists aren't. This is why the scientific method works, because other scientists aren't nice. Other scientists are gonna, and it's not because they're mean. They just want to get rid of all the garbage, basically. So they're going to make sure that and so yeah, some people say that this professor's so mean or that professor's so mean, but it's kind of since it's a self-policing kind of thing, it's kind of, and a lot of people, they don't have much time to, so they'll come off as unpleasant sometimes. It happens at conferences. Not everybody, but it's not because they're trying to be mean. They'll start picking you apart, basically. And so we just want to be. So anyway, you don't have to worry about this if you do use the chart method. And so the chart method is the way to go. In fact, you could just go ahead and skip the single replacement entirely and do all of the chart method, and then you'll be fine. Okay. All right. What we're going to do is an example of gas stoichiometry. And let's see.
Is this still like review?
No. Now we're going to go back to chapter 14. I got asked a question in the other class. We'll talk about it now. This is number 30. This is number 39, but I don't remember the exact numbers. So we'll just say similar to number 39. Ammonium nitrate solid. Ammonium nitrate solid, sometimes this can decompose into nitrous oxide gas plus 2 waters. This is a very high temperature decomposition, so it can form the water as a gas rather than as a liquid. And so ammonium nitrate solid doesn't take up much volume, but in this, so let's say even if we had a mole of ammonium nitrate is probably about, a mole of ammonium nitrate would probably take up a little jar worth of volume. So maybe 250 milliliters or something like that. And so a mole of ammonium nitrate doesn't take up much volume like this. But how much volume does a mole of gas take? A mole of gas takes like 25 liters, let's say, and then we have 2 more moles of gas. So altogether we form 3 moles of gas. 3 moles of gas would form about 75 liters under normal conditions. Now this is going to be at high temperature. At high temperature, it's going to take even more volume. And so it goes from a little jar like this to a big volume. And if that happens with a lot of energy and in a short period of time, then we get detonation or explosion. And so this is the decomposition of ammonium nitrate. It could decompose into other products as well, not just nitrous oxide, but it can decompose into the elements, other things. So this is just one way. Under certain conditions, it'll decompose like this. This would be like skeleton redox. Skeleton redox, you're told what the major products are. And so in the skeleton redox, we'd be told it decomposes and forms this and this. And then in the skeleton redox, all we're trying to do is balance it. So here, in this case, we'd split it up into half reactions and this type of stuff. This is a redox reaction, by the way. And this one we wouldn't get off the chart. The chart method, and a lot of redox are like this because conditions will change what you form. Like I was just reading. I was reading, the keyless cars. The keyless cars where you just push a button or to start it. They're saying that the number of deaths has increased dramatically from people forgetting to shut off the car after parking it in their garage. And so the amount of carbon monoxide deaths have increased like tenfold or something like that. Did you hear that? It was in the news yesterday. And so under certain conditions, you get a lot of carbon monoxide or this or that, unfortunately. And so that's the whole point of skeleton redox is just to try and see what happens versus predicting. When we use the chart to predict, our predictions might not always be accurate because the conditions might be just so where we don't get complete oxidation or complete reduction or something else happens. Anyway, this is a redox. This is what happens. This would have been kind of hard to predict. You could try predicting other oxides of nitrogen. There's lots. Like for example, in automobiles, it's hard to predict what oxides of nitrogen form. And so what they call it is NOx. Why do they call it NOx? Because they don't know. You're going to get a mixture. You're going to get nitric oxide. You're going to get nitrogen dioxide. You're going to get nitrous oxide. You're going to get a mixture of oxides of nitrogen, which they'll just call NOx. Depends on the conditions. And so this is the advantage of skeleton redox. Under certain conditions, we're going to form, let's say, nitrous oxide. This. Under other conditions, we might form nitric or nitrogen dioxide. Nitrous oxide. What's the oxidation state of nitrogen here in nitrous oxide? +1. Here it's +2. Here it's +4. We could go all the way to plus what? +5. Right? When nitrogen goes all the way to +5, let's see, would that be it? That's 6. No, that's not it. We'd have some other ratio of nitrogen to oxygen to worry about.
Did you say like nitrate?
Nitrate's +5, yeah. Nitrate's +5. All right, let's go back to this. So this reaction happens, and so let's say, just as an example, let's say the temperature was at 640 degrees C. And let's say, let's go with 50 liters of gas. No, let's make it simpler number. Let's say 90.0 liters of gas produced. Let's say the pressure of this is at 1.00 atmospheres. So 640 degrees C, 90 liters of gas in 1 atmosphere. How many grams of ammonium nitrate must decompose? cost this much product. And so we got 90 liters of gas, but you know, the gas is a mixture. And so there are two ways of visualizing this gas mixture. One thing that's always going to be the case is it has to form in a 1-to-2 ratio. If it doesn't form in a 1-to-2 ratio, then the atoms aren't conserved. And so for every 1 nitrous oxide, we have to have 2 waters formed. And so what do we do in this case for this? There are different ways of handling this. One way of handling this is by doing this. You know, for every mole of ammonium nitrate, we form how many moles of gas? 3 moles of gas. So we could use that as a ratio. So for example, we can get how many moles of gas, because the moles of gas doesn't depend on the identity. The moles of gas just depends on the pressure, the volume, R, and T. So if we know the pressure, volume, and temperature, then we can get the moles of gas regardless of the identity. Because does the ideal gas law ask you if the gas is nitrous oxide or steam? No. And so that would be the easiest way to do it. We set up a mole ratio where we just do generic gas, 3 moles of gas for every mole of ammonium nitrate. However, we were talking about Daltons, and we were talking about Avogadros. And so I want to do this in more detail. I want to figure out how many moles of each particular gas will form. And so, for example, this. If I have 90 liters of mixture, like this, 90.0 liters of mixture, this is going to be at 1.00 atmosphere here. And I have nitrous oxide, N2O, and I have water vapor. The water vapor, I'll show this orange here. And the nitrous oxide and water vapor will be at a 1-to-2 ratio. So I'll have twice as much water. And so that's always fixed. And so what we have is this. We have mole percent or fraction. And so the fraction of this would be, there are 3 parts total. And so the fraction would be, it's going to be 1/3 N2O by mole. And it's going to be 2/3, H2O by mole. And so, you know, for every 3 molecules, 1 will be nitrous, 2 will be water. As far as percentage goes, this would be 33% by mole N2O and 66.7% H2O by mole. It's a mole percent. That's always true, no matter what, you know. So if I have 100 moles, 33.3 will be nitrous and 66.7 moles would be water. Or if I had 100 molecules, you know, 33 nitrous, 67 water. But we can also visualize this mixture as a Dalton's mixture or Avogadro's. The reason we need this is because the ideal gas law requires that we use the proper pressure, volume, and temperature combination for each. And so we know that mole fraction or percent fraction is the same as the pressure fraction. And so if we look at this as Daltons, how would this look? How much nitrous oxide would I have? How many liters of nitrous oxide would I have? If we look at it Daltons, how many liters of nitrous oxide do I have?
Which is 100 liters?
Well, we have 90 liters total. So out of this 90 liters total for the mixture, how many liters of nitrous oxide do I have if I'm thinking Daltons? It would be 90. And so if I'm thinking about Daltons, I'd have 90.0 liters of nitrous oxide.
For every
What would the pressure of the nitrous oxide be?
0.33
Yeah.
atmosphere with
Yeah, exactly. It would be 0.333 atmospheres. Good. And then how many liters of water vapor would I have?
it. So 90.
I'd have 90 liters of water vapor too. And this would be at 0.667 atmospheres. Okay, so here I could figure it out. You know, the moles of N2O, will be equal to the pressure of the N2O. Here the pressure is going to be 0.333 atmospheres times the volume of N2O. Here the volume is going to be 90.0 liters divided by R times the temperature. Well, the temperature is going to be the same for all the gases. It's going to be 640 degrees C. And then the same thing, if I want the moles of H2O, I can figure it out. The moles of H2O will be the pressure of the H2O. The pressure of the H2O is 0.667 times the volume of H2O. Volume of H2O is 90 liters divided by RT. And so I could use stoichiometry here. So for example, if I want to figure out how many moles of ammonium nitrate, I could use, there's no limiting reagent here because these are produced from here. And so I could use either nitrous or water. And so for example here, what I could do is I could just go from the volume of nitrous. Here I'm not going to use the molar volume because it's probably just easier just to use the ideal gas law here. So from the volume, I'll go to the moles of nitrous. And from moles of nitrous, I'll go to moles of ammonium nitrate. And from moles of ammonium nitrate, I can go to grams of ammonium nitrate. And so here I just use ideal. Or, likewise, I could have used water. I could have gone from the volume of water either, or to the moles of water, because I know the pressure, the volume, and temperature. From the moles of water to the moles of ammonium nitrate, and I would get the same answer. Either way, I'd get the same answer because both products are produced stoichiometrically. They have to, otherwise we're... And so either one or two, but not both. One or two. Could do that. That's if we visualize this as a Dalton's mixture. However, if we visualize this as an Avogadro's, how would this picture look different? So if we do this as an Avogadro's, then how many liters of nitrous did I make?
33.3.
Yeah. In other words, 1/3 of that, actually not 33.3. 33.3 would be if I had 100 liters.
Oh, whatever. 33.3.
Yeah.
90.
In other words, the pressure fraction, we said, the pressure fraction is the same as the mole fraction. The volume fraction in Avogadro, that's for Daltons. For Avogadro's, the volume fraction is the same as the mole fraction. So 1/3 of the volume will be nitrous. 1/3 of 90 liters is, this is why I picked 90. It's going to be 30.0 liters. 1/3. 2/3 will be water, yeah. So 60.0 liters. I did this just to mix it up, because if everything's 100 or 1, then you're right, it would be 33.3 or 0.33. But you got to be aware, it's 1/3 of the total volume. The total volume in this case is 90, or it'd be 1/3 of the total pressure. I didn't have to start off with 1 atmosphere. If I started at 1.2 atmospheres, it would have been 0.4. That would be 1/3. So be careful with that. And so this is 30.0 liters of nitrous oxide. Okay, so that's the volume. What's the pressure of the nitrous oxide?
1 atmosphere.
Yeah, 1 atmosphere. And so what I would do here is, if I want to calculate the moles of nitrous oxide, the moles of nitrous oxide are going to be equal to the pressure of nitrous. The pressure of nitrous is 1 atmosphere times the volume of the nitrous, and the volume of the nitrous is 30 liters divided by RT. You know what? We're going to get the exact same answer here in Avogadro's as we would get in Dalton's. Exact same answer. That's because this is two ways of looking at it. The problem is when people do both simultaneously. So what happens is this: people will cut down the volume, so they'll say 30 liters of nitrous, but they'll also cut the pressure. And so a common mistake here is that they'll try to do simultaneously Dalton's and Avogadro's. So they'll say there's going to be 30 liters of nitrous oxide at 0.333 atmospheres. That can't work. And so it's one or the other. You can't have both simultaneously. So this is going to be 60 liters of water vapor at what pressure? 1 atmosphere. And again, we'd get the exact same answer. And so we could use either Avogadro's or Dalton's. Often with stoichiometry, we use Avogadro's. When we collect gases over water, we use Dalton's. But we could use either. All right, so that was an application of, and this was only a problem number 39. The reason I brought this one up is because I thought this is more of an advanced problem rather than a basic problem. So if you look in your book at number 39, that's more of an advanced. And it should have been higher. All right, let's continue with solutions. If other questions come up with stoichiometry, I didn't go through very many examples. In fact, 0, pretty much other than the ones on the PowerPoint. So if any other questions come up, let me know. Last time we left off with this slide, we're looking at dilute. The dilute copper solution is light blue. Sometimes this is so light you can't even see the color. You need a certain concentration to be able to detect the color, even if there are copper ions in there. So sometimes people think there's no copper because it's almost colorless. Here it's easy to see. There's lots of silver floating out. Did we finish the chemical reaction for this? Yes. You know, this one, how did we do it? Did we use the chart method or the single replacement? Yeah, we used single replacement. So this was the A plus BX. Why did I do this? Why I did this is because of this. You know, what's the strongest reducing agent present? Well, as far as reducing agents go, you know, I would look at the species I have. This is what I do mentally. Copper, I'd have silver ions, I'd have nitrate, and I'd have water. So I do a quick mental inventory of what I have. What's the best reducing agent out of these 4? Maybe I better bring up the chart. What's the best reducing agent on the chart? Lithium. And so I'd go up. Does silver ion and nitrate occur on the lithium side? No, it's between copper and water. So what do you think is a better reducing agent, copper or water? Copper is a metal. metals tend to lose electrons. Water, is water easy for it to lose electrons? No. It's hard to oxidize water. And so copper is the best reducing agent. Well, that's what single replacement predicts A is the reducing agent, right? And then B should be the oxidizer. Well, silver ion is a good oxidizer. Silver ion is this is why it stains everything black, because it tries to oxidize everything. So silver ion is a good oxidizer. Good oxidizer. And I'd expect it to be way better than water. However, is it better than nitrate? Yeah, we're missing the H plus. If we're missing the H plus, then its ranking drops way down. And so it's not going to be so great anymore. And so since we're missing the H plus, then that means silver ion's the best. This is why I went straight into single replacement, because why single replacement's easy. A plus BX yields AX plus B. And so copper goes to copper 2, not copper 1. I think I asked you this before. And so mentally I already saw that single replacement should work for this, because A is the best reducer and B is the best oxidizer. If you're uncertain, then you do the chart method. If you can't answer that question, do the chart method. And so we did single replacement for this particular reaction. Well, we're dealing with aqueous solutions, so let's move on here. Tiny crystals of silver look black. That's why things get stained black. But you can see bigger crystals like these needles here have the silver color to them. So this almost looks like a black fuzz. But here's some nice crystals of silver. This is dendritic pattern. Looks like trees, branches. We talked about solubility. There's two definitions of solubility. There's one, will it dissolve or won't it dissolve? Do you remember the solubility rules? The solubility rules are if more than 0.1 moles dissolves in a liter, then we call it soluble. And so solubility rules, that's the cutoff for our solubility rules. So greater than 0.1 moles of solute. Solute is, what we're trying to dissolve in the solvent. So the solute would be the salt, the solvent would be water. If more than 0.1 moles of solute dissolves per liter of solution, then soluble. If less than 0.1 moles, then insoluble. If about 0.1 moles dissolve, then we give it a different name. If about 0.1 moles dissolves, we call it slightly soluble. So we give symbols for these. Soluble is S, insoluble is I, slightly soluble is SS. Slightly soluble. That's the rules. We also have something called the solubility. Well, it's the same word, but a different meaning. This is the quantitative definition. The quantitative definition is the maximum amount of solute. Maximum amount. of solute that dissolves in a given amount of solvent. So we see both of these definitions play. Let's just take a look at some data here, maybe. So we see both definitions at play, I think, in this one. Here, they say lead 2 chloride is an inorganic compound, which is a white solid under ambient conditions and is poorly soluble. Poorly soluble, it's insoluble. But what does insoluble mean? Insoluble means that less than 0.1 moles will dissolve. That's qualitative. And then we go, well, if less than, well, exactly how much dissolve? Exactly how much dissolves is called the quantitative solubility or just the solubility. And so if you want to know the solubility, that is how much dissolves, well, 10.8 grams of lead 2 chloride will dissolve in a liter. And, well, that's a lot, that's like 11 grams. So is that really insoluble? Well, it's insoluble according to our definition, which is kind of a loose definition. And so it's not that much, because table salt, you know what the solubility of table salt is? Okay, that's 11 grams in a liter at 20 degrees C. If we look at table salt, table salt, they say, is soluble. Well, it's soluble more than 0.1 moles dissolve. But if we look at table salt, 11 grams of lead 2 chloride dissolves per liter, 359 grams of table salt dissolves. But you go, well, only 359? Why can't they dissolve more? I want to dissolve 500. Is it possible to dissolve 500? No. What's going to happen is if you try to dissolve 500 grams of table salt in a liter, only 359 of that will dissolve. The rest will remain as solid. And the rest is, what we say is that we've saturated, the solution. So normal table salt will dissolve, but that's a heck of a lot of table salt. And so we have to draw a line somewhere, and the dividing line is this. It's kind of arbitrary, because somebody might say 11 grams, that's more than I want to drink, So this is why, where is it? There's another story I read that they're, at some place they're going to turn off the drinking water fountains. I think in the national parks. Did you hear about that? The story came out this morning about, the headline of the story is that you're going to have a harder time finding a drinking fountain or drinking water because a lot of parks are turning off the fountains because of lead. So lead's fairly it's fairly insoluble, but who wants 11 grams of lead in a liter? 11 grams of lead chloride or whatever it is.
Did you change the solubility of, or can you change how much solute can be dissolved in the solvent by changing the temperature?
Yes, right. So if you go to Wikipedia doesn't show this, but most books show this. The solubility in cold water, room temperature, and hot water. And so by changing the temperature, you can change the solubility, sometimes dramatically change the solubility. So this is why we used ice bath. We used an ice bath earlier to decrease the solubility, to try to get more crystals to come out. We use temperature to heat it, to dissolve the crystals, to get it to, so we use it all the time, temperature. There are other ways to change the solubility too that involve chemical reactions. And that's more on Chem 1B. So for example, gold. Gold is insoluble in water. Gold happens to be insoluble in nitric acid too. You know, nitric acid, if we do single replacement or we do chart, it doesn't dissolve. But gold turns out to be soluble. Did I talk about this before? In aqua regia. Aqua regia is a mixture of nitric acid and hydrochloric acid. The purpose of nitric is an oxidizer. The purpose of HCl is an acid base, but it's not an acid base that you think. It's chloride. Chloride is what we call a Lewis base. And so the HCl is added. We could add sodium chloride to do the same thing because we want chloride. We don't want the H+. We want the chloride. And the chloride does a Lewis acid base reaction with gold ions to help stabilize it. And so this is a two-part reaction. The first part is oxidized, but you know we need a little extra push, a little extra drive to get it to oxidize. And that little extra push comes from the chloride. And so this would be a little more advanced. This is trying to use chemical reactions to dissolve things that aren't so soluble. Gold's not soluble. Aqua regia dissolves gold. So the nitric acid does the oxidizing. What they did was they combined it, and then the chloride attacks the gold 3 ions. Chloride attacks the gold 3 ions to make this thing called tetrachloroborate. These kind of weird species here we look at in Chem 1B, not in Chem 4. So the first step is we've got to oxidize the gold from gold 0 to gold 3, and then gold 3 is unstable. And so we stabilize the gold 3 by attacking it with chlorides. That's how aqua regia works. A combination of reactions. Redox. Here, you know, the nitrate goes to NO2 to the brown gas. There are other reactions that we don't always get. You know, so for example, when we do use nitric acid in the chart, when we do use nitric acid in the chart, do you see we form NO? NO is a colorless gas, nitric oxide. It's a colorless gas. But NO NO in air is exposed to oxygen. And oxygen easily oxidizes NO to NO2. This would be like a skeleton redox. This is not on the chart. And so it goes from a colorless gas, a CCG, to a brown gas. This brown-orange gas is what you see because this happens pretty much automatically. And so, you know, on the Texas City video, the guy they were interviewing said, you know, and some of the other witnesses said there was a beautiful orange gas being generated. That beautiful orange gas is NO2 being formed when the NO reacts with O2 in air. And then the guy was saying there's a sulfur odor in the air. It wasn't a sulfur odor, it was a NOx odor, which has a sulfur type odor. And they were breathing NO and NO2, which has that sulfur type odor. Texas City. that's chemical. This is physical dissolution. This is chemical dissolving. When we're dissolving it with water, that's a physical process because it's reversible. When we dissolve it chemically, it's not easily reversible. So this is just physical solubility. We have to distinguish between physical solubility, like sugar water. You evaporate the water, you get sugar back. But if you take aqua regia and you evaporate the water, you're not going to get gold back. You're going to get the gold salt back. Then chemically, you have to convert that back into gold. Okay, we have saturated solution. Saturated solution would be of sodium chloride would be 359 grams in a liter. You can't dissolve any more. It would be called saturated. Unsaturated is if you have less than 359 grams per liter. That means more. This would be like humidity. Saturated solution would be 100% humidity. Unsaturated would be less than 100% humidity. And the level of humidity depends on the temperature. It's the same thing with sugar. You can get more sugar in water at higher temperature than at lower temperature. Supersaturated. Sometimes it's possible to get more than 359 grams. And so what happens with supersaturated is this. At high temperatures, typically things are more soluble, solids, not gases. Gases at low temperature are more soluble. But most people have experience with the supersaturated gas in liquid solutions. And so if we look at a carbonated beverage, like a soda, something like that, there's some gas in there. So there's a little bit of gas and the rest is liquid here. Do you know what that gas is inside a soda bottle? Is that air? Maybe high pressure air? Yeah, it's carbon dioxide. The gas is carbon dioxide. And they want pure. And so it's carbon dioxide at 1 atmosphere. And so what happens is if you have carbon dioxide at 1 atmosphere, the CO2 molecules are being forced into the liquid. At the same time, CO2 is being evolved out, and we reach some sort of dynamic equilibrium. And so we got CO2 being dissolved and CO2 being evolved out of solution, or undissolved, I guess. If you open the cap, though, what happens? Do you know what the CO2 level in air is? Let's use Dalton's law for this. If we look at CO2 in air, actually I have it here, let's see. Maybe I don't, maybe I put it. Well, let's take a look here. By volume, dry air contains 78.09% nitrogen, 20.95% oxygen, 0.93% argon, and 0.04% carbon dioxide. 0.04% carbon dioxide means if I had 100 atmospheres of air, I'd have 0.04 atmospheres of CO2. And so if I open this cap, and then the CO2 escapes out of here, and the air goes back in. So this is exposed to air. Well, air consists of, if I had 100 atmospheres, it would be 0.04 out of 100 atmospheres. And so, in other words, this would be 0.04 0.0004 out of 1. And so if I have 1 atmosphere of air, then I have 0.0004 atmospheres of CO2. And so this is pure CO2. Pure CO2 is going to be at 1 atmosphere, so I have 1 atmosphere of pure CO2 forcing its way into the liquid. If I open this, then I'm going to go from 1 atmosphere all the way down to 0.0004 atmospheres. And so now the what we call degassing rate is going to greatly exceed. And so what happens is the only way I can maintain large concentrations of CO2 in this liquid is by having CO2 at a high pressure. I have high pressure CO2. Once this turns into air, then the CO2 pressure drops. Let's see, how many orders of magnitude? Like 10,000 times smaller. And so what we end up with is supersaturated solution of CO2. We have way too much CO2 in there than it can withstand, and that's going to degas. Does that make sense? Well, we could do the same thing with sugar water. If we have hot sugar water, and then we cool it down to cold sugar water, hot sugar water can hold a lot more sugar. When we cool it down to cold sugar water can't hold as much sugar. And so what has to happen to the excess sugar? What has to happen to the excess sugar is a process called nucleation and growth. Have you ever heard of nucleation and growth? Nucleation and growth means that if I want to get rid of excess sugar, the first thing is I have to nucleate a sugar crystal. That is, the sugar crystal, one sugar molecule has to pack with another to start the crystal. And so we need to start the crystal. And the crystal has to grow. Sometimes nucleating crystals isn't so easy because the molecules don't pack together so nicely. And so sometimes, everything has to be perfectly positioned to form a crystal. And if one molecule is slightly off and it's hard to position it correctly, then there's sluggishness in nucleation. And so what happens is if there's any kind of sluggishness in nucleating crystals and growing them, then we're going to end up with a supersaturated solution, which we have too much. So we have to wait. We have to wait until they find the right position, and then they can start crystallizing and growing. The same thing here. This is going to remain supersaturated because CO2 bubbles have to nucleate and then grow. And so CO2 bubble nucleation is sluggish. CO2s have to gather together and generate enough of a bubble to rise up through here. There are ways to speed up nucleation and growth. Do you know one way of speeding it up? People use Mentos to speed it up. Have you seen that? Mentos?
Oh, that's funny stuff.
Well, let's see if there's. Okay, so they open it. It used to be pure CO2. They open it to air. Now the CO2 is way down. And so there's still too much CO2. You can see some CO2 nucleating and growing there. But there are certain things that will speed up the nucleation of bubbles. There are certain things that will speed up the nucleation of crystals. One way is to use seed crystals here. One way to speed up bubble formation here is to use Mentos, which those Mentos fountains aren't so big. Alright. Maybe I picked the wrong video here. I just wanted a simple one, sorry. Find a simple one. Maybe this one's the best. Yeah, I have to get off Nancy. So right now, the CO2 is somewhat, it's called metastable because let's wear some safety goggles. You guys have seen this, right? Mentos fountain. Should use diet. Everything's gonna get
I'll
stuck.
just hire back 14 interesting.
Yeah. Too bad.
Well,
Yeah, so we could have supersaturated. If there's sluggishness and nucleation and growth, we can form supersaturated solutions. So, One thing that's hard to form crystals is sodium acetate. It's because of the acetate ion. Sodium acetate is notorious for forming supersaturated solutions because nucleation of the crystals is difficult. And so the acetate anion, looks like this. The acetate anion has to be perfectly aligned with the sodium ions to nucleate new crystals. This is not a 3D. 3D, this would be tetrahedral, this is trigonoplanar. So acetate's hard to nucleate. So let's take a look at this. So you heat up a hot solution of sodium acetate and then cool it down. As you cool it down, the solubility decreases dramatically, but it's not nucleating. It's not nucleating because it needs something. And so that's a C, that's a surface where the crystals can nucleate and grow. And so it needs just any surface, like scratches or whatever else. And so you can see these needle-like crystals growing now. And so it just needed a little bit of help for nucleation. Growth is fine. Nucleation. And so oftentimes people will use seed crystals. This person is using their fingers to help nucleate growth. I haven't done that. Let's see.
Hello, today I have for you a wonderful experiment, holding ice. This experiment can be...
So it needs some
used by
surface for the
anyone.
crystals to start to grow.
We need the vinegar and baking.
That's sodium acetate. Vinegar is acetic acid. Baking soda is a base, so you can make sodium acetate. Sodium bicarbonate is baking soda. So you could do this at home if you want. This is another one. This is a seed crystal on a petri dish. Those are the sticks, toothpicks to seed. Also, it's very exothermic. They're using a nail to seed it. It has to be very clean glass and there can't be any dust.
Okay. That's like constant touch.
Yeah, it's going to be hot. Dissolving sodium acetate is highly endothermic. This is a seed crystal. There's a huge difference in the solubility in hot water versus cold water.
What is the solution they're using?
Sodium acetate. Sodium acetate you can make from vinegar and baking soda.
So you just mix vinegar and baking soda together?
Yeah, and then you have to evaporate all the water.
So you just heat it up.
Yeah, in fact, you dissolve a huge amount of sodium acetate in a tiny bit of water by heating it up. you heat it up, it doesn't melt, it just dissolves. It dissolves in a tiny bit of water. And then when you cool it down, then it can't sustain it because there's a gigantic difference between the solubility in hot water versus cold water. Sodium acetate's like that. Other salts aren't so dramatic. So sodium acetate's very dramatic.
That's very cool.
Yeah, so if you look at if we go look at the Wikipedia, it probably shows it. Sodium acetate. Take a look at the difference in solubilities at the different temperatures. So if we, at room temperature around 20 degrees, we could dissolve 123 grams of sodium acetate per 100 milliliters. But if we warm it up to close to 100 or 100, you could dissolve 162. And so we're going to have like 40 grams too much. And so what we do is we heat it up to 100, we saturate it, and then we cool it back down. We're going to get 40 grams too much sodium acetate. That 40 grams has to crystallize out or precipitate out of solution. And so that's what you're seeing with these. What's anhydrous? Trihydrate is about 40 grams. They also show solubility in alcohol, solubility in hydrazine, and solubility in sulfur dioxide, solubility in methanol. It's pretty soluble in methanol. Solubility in ethanol, a lot less. Solubility in acetone. So there's a lot of different solubilities there. It works best in water. Some things have no solubility limit. Some things are infinitely soluble, and so there's no limit. Sodium chloride is not infinitely soluble, but methanol is. If I try to dissolve methanol in water, there's no limit. I can dissolve any amount of methanol in water I want without limit. That's called miscible. And some things don't dissolve at all, like oil. I can't dissolve any oil in water, and so we call it immiscible. Immiscible.
You said like there's a mixture of a bunch of other stuff too. Isn't like, because oceans technically they call it salt water, right? So but does the salt that makes like the ocean stuff salty? Is that like a mixture of other things too? Because it's not like putting like sodium chloride in water. Like
No, this ocean water has lots of salt. In fact, there's did you know there's gold in the ocean? Well, the ocean water, the composition varies depending on what ocean you're looking at. A lot of metals are mined, like magnesium. You know why magnesium comes out of the ocean?
yeah.
So ocean water composition. Well, one of the ideas people had was, why not mine gold out of the ocean? I have a more accurate chart of this I can bring in. But yeah, there's a mixture. Potassium salt, sodium salt. So sea salts are a mixture of salts. Magnesium, calcium, potassium, sodium, and other salts. Chloride. These are just looking at the major components. Let's look at some of the minor components. So let's go with gold in seawater. Is it because gold is soluble? are 20 million pounds of gold, they estimate, in seawater. 20 million pounds of gold in seawater. But 20 million pounds only makes it parts per trillion. So I guess there are 13 parts per trillion, which is hard to extract. Whereas the magnesium composition is much higher. So get it out. But the gold is going to be in a not pure metallic gold form. It's as a gold ion, stabilized by other things. So let's see. Researchers fishing pure gold from seawater. Uranium, gold, lithium, and salt water. Billions of tons of valuable raw materials are dissolved. Previously, it was difficult to extract them. Now researchers are venturing again into fishing the treasures from seawater. Germany, the sea is a gold mine. And so, yeah, there are lots of things in seawater. Lots of things dissolved, including oxygen. If there's no oxygen dissolved in seawater, marine life couldn't exist. CO2, etc. And all that there's some kind of balance. They're talking about the coral right now. Things destroying coral and other things. So there's a balance in the water chemistry, the oceans. Well, billions of tons of uranium, now even more, because they dumped all that nuclear waste into the ocean. What's that? Oh, at the Fukushima nuclear power plant, a lot of the cooling water was dumped into the ocean. The cooling water was heavily contaminated with radioactive isotopes. So this is kind of interesting. In the 80s, Japanese scientists experimented with materials that specifically find uranium in seawater. So they need this research now. About plutonium and uranium. After 49 days in seawater, the cords were tied together. The researchers had extracted 2 grams of uranium per kilogram absorbed from the sea. Wow, 2 grams of uranium is a lot, actually. Oh, this is an interesting article. This might be pertinent today. So uranium, lithium for batteries. Interesting. When was this published? 2016. Here's sodium acetate here. This is the seed crystal they're using. The seed crystal they're using is fast because then the sodium acetates ions can attach to this and grow like they are here. This is admissible and immiscible. Light dissolves light. So if we have octane and oil and carbon tetrachloride, these are like mixing 2 oils. Mixing 2 oils is no problem. They like to mix. If we look at this has what type of intermolecular attractions? Well, these are octanes. So between 2 octanes are nonpolar, so we have London dispersion. Between 2 carbon tetrachlorides, these are nonpolar as well. We have London dispersion. So we're breaking London dispersion, we're forming London dispersion. So these things can intermix, no problem. However, water and gasoline is a different story because in order for these to mix, we break the London dispersion, we break the hydrogen bonding. Well, hydrogen bonding, water doesn't want to break that. So water is not going to break apart to allow these in because for every 1 octane that it allows in to solution, it would have to break a large number of hydrogen bonds. Well, energetically, that's not favorable because these are strong dipole and these are weak dipole interactions for a given size. And so miscible versus immiscible. Whereas methanol is no problem. Methanol is totally miscible. because methanol, we end up breaking hydrogen bonds, but water, we end up breaking hydrogen bonds, but we reform hydrogen bonds because methanol hydrogen bonds with water. And so methanol is totally miscible with water. So, polarity is very important in this because light dissolves light. We're looking for polar dissolves polar, nonpolar dissolves nonpolar. And so we're looking for molecular polarity, that is, we want to look for negative and positive ends of the molecule. Ions are very polar. Ions are monopoles because they're either positive or negative. So ions are highly polar. So we're looking at solution formation here. In solution formation, we just looked at this. The forward arrow here is called dissolving or dissolution. So if we take solid sodium chloride, we can dissolve it in water. We need water to form the aqueous ions here. So dissolution. The reverse process is called crystallization or precipitation. And what happens is if we try to dissolve 500 grams of sodium chloride, not all 500 grams will dissolve, but we call it dynamic equilibrium. Equilibrium because only 359 grams will dissolve. Dynamic because this never stops. Crystals are always dissolving. Crystallites are always forming. The crystals dissolving, crystals forming. It's dynamic, but there's no net change. There's zero net change because only 359 grams dissolves, but the stuff that remains undissolved will start to look different. So this is what we have here. We're going to saturate the solution here with sodium ions and chloride ions. When we saturate, we'll have a total of 359 grams worth of sodium and chloride ions per liter. Whatever excess there is will remain undissolved. But that excess, let's say I tried to put 500 grams, that excess would be 151 grams. That 151 grams doesn't sit there. That 151 grams continues to dissolve, but what we have is we have such a high concentration of ions here, they continue to crystallize. And so crystallization happens at the same rate that's called the dynamic equilibrium. And we have no net change. These ions here, look how they're surrounded by the water molecules. You see that? They're surrounded. Do you see the difference in how they're surrounded? Like, for example, the negative ions are surrounded by what end of the water molecules? The hydrogen end. Because the hydrogens are positive. And so the positive hydrogen ends help stabilize the negative charge here. This is called a hydrated ion or a solvated ion. Hydrated ions are stabilized due to the electrical attraction between water and the ion itself, monopole of the ion. If you look at a positive charge, the positive charges are stabilized by the oxygen end of water. The oxygen is sort of negative, so we get a negative positive charge. So these hydrated ions are stable. This is the dynamic equilibrium. So this is like humidity. This is like supersaturated versus whatever. Well, anyway, initially this is pure water, and so we just have dissolution occur. As the water gets saltier and saltier, crystallization will take place. Eventually we'll get to a point where it reaches a certain concentration where the collisions with the surface here equal the dissolution off the surface. And so in other words, where dissolving equals crystallization, and then we reach a state of equilibrium, there's no net change, but there's always change. These crystals are always dissolving and new ones forming. So if I tried to put 500 grams of sodium chloride, this would be 151 grams, but if you look at it with a microscope, and you look at a crystal, that crystal's going to disappear, and a new one's going to appear in its place. And so the crystals are always changing, but we'll still only have 151 grams. So factors that determine solubility, what makes something highly soluble, what makes something less soluble. And so things we look at are the types of intermolecular forces and the strength of those. Things that are strongly bonded together are less soluble. Things that are weakly bonded together are more soluble. And then we need the type of interaction, like polar versus non-polar, like dissolves light. And then these two factors, pressure and temperature. Pressure affects the solubility of a gas, like CO2. Temperature affects the solubility of solids and liquids, like sugar and water. Temperature also affects the solubility of a gas. At high temperatures, gases become less soluble. At high temperatures, solid solutes become more soluble. So they have an opposite effect. Ethylene glycol and water are miscible. Ethylene glycol has a lot of these OHs. This is ethylene glycol. A lot of OHs means lots of hydrogen bonding. And so the waters can hydrogen bond to ethylene glycol. Therefore, it's miscible. So the antifreeze is ethylene glycol. However, oil's not. The water doesn't want to break apart to make room for oil. So oil is just going to float on the surface here. So the oil is less dense, so it floats on the surface. Water is going to stay together. Oils will stay together. Here they'll freely mix. So this is like dissolves light. It should have been on this slide. I don't know why they didn't put it on this slide. The type of interaction. Here it is. This is what we call Henry's law. The higher the pressure, the more gas molecules will be forced into liquid. And so here's a gas at low pressure. Some molecules get forced into liquid here. Here's a gas at higher pressure. At higher pressure, more molecules get forced. And so this is like CO2. In air, CO2 is 0.0004 atmospheres. But when they manufacture these carbonated beverages, they increase the pressure from 0.004 atmospheres to 1 atmosphere. And so here we have a lot of CO2 pressure here. It's going to force a lot of CO2 molecules into liquid. Temperature and solubility. Most salts are more soluble at high temperature, but not all. So for example, lithium sulfate is less soluble at high temperature. But sodium chloride is more soluble, potassium chloride, ammonium chloride, lithium chloride, rubidium chloride, sodium nitrate. These species become more soluble. Sodium acetate is like that too. Sodium acetate is much more soluble at high temperature than low temperature. 40 grams more. So sodium acetate would start here and then like up here. Here they have ammonium chloride in warm water, and then they cool it down. And you can see solid ammonium chloride crystals in there. Ammonium chloride seems to nucleate and crystallize easily, so just by cooling it, crystals form easily.
What makes the lithium sulfate less soluble at higher temperatures?
Well, one of the things is whether it's an endothermic or exothermic process. And so for dissolving lithium sulfate, it turns out to be exothermic. Exothermic means that when you dissolve it, it actually becomes more stable, something like that. And so when you heat it, it doesn't. So there's a conflict. And so what does that is because of the lithium ions. Lithium ions, it's not because of the sulfate, because other sulfate salts behave like you'd expect. Lithium ions are kind of unusual. Remember we were talking about why is lithium the number one reducer? Shouldn't it have been cesium? Do you guys remember that talk at all? If you look at the periodic table, which atom should lose its electron easier? Should it be a gigantic cesium losing its electron, or tiny lithium? Which one would be easier for an oxidizer to strip an electron off of? A gigantic cesium. So cesium should be the number one reducing agent on the chart. The reason why cesium isn't is it's because lithium is a heck of a lot less reactive than cesium. The only reason that lithium is at the top is because of this. Lithium is way less reactive, but in the long run, it's more stable in solution because lithium ions are very small. This is the only reason lithium's at the top. It shouldn't be. Lithium shouldn't be. Lithium's compared to cesium. Cesium is way more dangerous, than lithium. Way more. But in the long run, over a long period of time, lithium produces more energy, and that's because of this. The lithium ions are tiny. Lithium ions being tiny, they're easily hydrated by the water molecules, and they form very stable hydrated ions. And so that's the only reason why the difference. If we ignored the hydrated ions, then lithium would be a lot less reactive. Does forming hydrated ions cause an explosion? No. Taking electrons causes an explosion. So this is why cesium is much more explosive. But forming hydrated ions is like a slow release of energy versus a rapid release of energy. So let's see lithium. But you don't have to, you just memorize the general trend. The general trend is higher the temperature, the higher the of solids. What about for gases? Let's say, okay, you have a fish tank. What's going to happen if you increase the temperature of a fish tank? Are you going to get more O2 or less O2 in water? Or let's say you have a soda. If you heat up the soda, you're going to lose all the carbon dioxide. It's just going to degas quicker. And so the same thing happens in an aquarium. If the temperature gets too hot, there's not going to be enough oxygen for your fish to live. And so the same thing with soda. If you heat this up, so it's the opposite. It's the opposite for gases. If we're looking at gases, the higher the temperature, all gases would point in the reverse direction. The higher the temperature, the lower the solubility for gases in water. So let's look at the composition, of solutions. Solutions are mixtures. We express the composition of the mixture in different ways. The composition of the mixture can be expressed as percentages of molarities or whatnot. So we have a mass ratio. Mass ratio is called mass fraction. Mass fractions we can convert into a percentage by multiplying by 100%. So if we have a mass ratio or mass fraction times 100% gives us our percent by mass. So 50% means 50 out of 100 grams, something like that. And so we did percent concentrations by masses all the time. Well, it's going to be the mass of the solute, what we're looking at, over the mass of the solution. The mass of the solution is the mass of the solute plus the mass of the solvent. That is, it's the total mass. And so it's the mass of component A over the total mass times 100%. That's how we look at percentages. So when 125 grams of a solution was evaporated to dryness, 42.3 grams of solute was recovered. What was the percent concentration of the solution? So it's 42.3 grams out of 125. And so we want to convert that into percentage, get that into fraction, and then just multiply by 100. So we'll take the mass fraction. Mass fraction is 42.3 out of 125 times 100% gives us 33.8% by mass. Okay, I guess we're just about out of time. So we'll probably stop it here. We'll continue with chapter 16. See how much more. Chapter 16 is a long chapter too. Wow, Chem 4 is a lot. It's a long chapter, isn't it?
Can you post this on Galaxy, please?
Yeah. Okay. Do that. Post them right now.
Are you gonna post practice exam for the final as well?
Not for the final. Let's see if I can. Well, I'll try to find a exam 4. I'll post that.
Do you know what the exam you have?
This is homework. Up to a certain section. Like for example, homework for exam 1 goes to gas.
So you mean like on you? So you already have grades on?
No, this is a progress check.
Oh, okay.
You
So
still
that's
have
not like
to-
the grade for it, that's
No.
just what I've done so far?
That's what you've done so far. I want to check it.
Okay.
If you've done more, then you'll have a higher score than that.
Okay, so that'll update.
Yeah, that'll update by at the end of the semester when I'll give you your final grade for your homework. So as long as you get all those done by the end of the semester, then you can get it.
Perfect, thank you.
Have you looked for the what's the grade you had?
Yours?
Yeah.
What did I put on yours? 10?
It was 10 out of 20. I got half of it.
All right, then it's 10 out. You did it, right? You turned it in. All right. I haven't then. As long as you did all of it. You did all of it?
Yeah.
I'll update yours.